In this video, we will be working through Chapter 2 of the XPDrainage introductory tutorial. As one might imagine, Chapter 2 will be picking up at the end of what has been done in Chapter 1. At this point in the project, we have imported inflow areas into this model, as well as connections and ultimately a pipe network. All of the inflow areas are associated, as we can see here, with junctions within the network. At this point, we need to expand this preliminary pipe network into a real-world system. So what do I mean by that? Let's take a closer look. So this pipe network and this drainage system all drains down through this lower point. We'll see I have this object highlighted here. This is actually a dummy object. Not a very nice name, I know, but that's something that's used for shorthand for kind of a made-up object. So often when working in CAD or working in GIS, these can be limited systems when trying to represent and assess stormwater designs. So in most systems like CAD, when we begin to lay out a pipe network and a stormwater treatment train, there aren't any outlines, as we'll see we can use in XPDrainage, to guide our assessment. So those tools are limited to only using links, right? These lines, we're going to call connections, or these nodes are points. So in CAD, what really is supposed to be an underground detention system is represented simply by this one dummy point. What we can do in XPDrainage is we're going to change the template that's used. So following the tutorial, we'll right-click on this object, and we can select Change Template. We have a list of all of the different template types for stormwater controls that are in the software. I'll select one that says Arch Chamber. We can even change the name to say Arch Chamber. Lo and behold, we have a shape which appears. So let's take a look at what we've just done. We've changed that dummy object, right, that made-up placeholder, so to speak, if we were working in CAD, to actually representing what will go in the ground. This is a real strong point of XPDrainage, is that we're going to actually design and assess what will be in the ground and how it will be connected. As we can see here from this diagram, a typical proprietary arch system has been designated, and we can look at perhaps a section profile. We'll notice what we're calling embedded parameters. There's fill above, fill below. So in XPDrainage, the realistic storage and attenuation and hydraulics which will occur through this facility will be taken into account. One item we need to add, since we've converted this dummy point, is we need to add an outlet from this system. So we have this pipe network draining to this chamber detention facility, and we need to switch our outlet type to orifice. Again, following the tutorial, let's change the invert level to be 1.5 feet above the base of the facility. So in that case, we'll change this to 167.3, and we'll have a 6-inch diameter outlet. So in this case, 0.5 feet. Click OK. So now we have a realistic representation of our stormwater control, this underground detention facility, though we still aren't realistically representing how these pipes will drain to that system. So the first thing we're going to do is right-click, and we can say Specify Inlet or Outlet Location. As we can see in XPDrainage, we can actually place the inlet and outlet points for this facility. So in the real world, these pipes will daylight out into this part of our facility. Similarly, we have an outlet location. I will move this around just for clarity's sake. Perhaps this is the outlet, which drains into our city trunk line. So now looking back, we have a representation of this real system, how it will actually be constructed. We'll get the true lengths and slopes of these pipes. So when we design and when we assess, we're assessing it as built, so to speak. This is truly unique to XPDrainage and truly something we would say is paramount to achieving a successful project outcome. There's one more item to note. I mentioned before how these inflow areas are automatically associated to a junction. Well, the software is pretty smart, but perhaps isn't right all the time. You'll see automatically it associated that this parking area would drain to perhaps this manhole. Well, that's not the case. In the real world, there's going to be an inlet grate in this parking lot. So I could right click on the inflow area and say reconnect. And I can place this inlet point where it truly will be constructed. So let's get a sense for what we have put together so far. I want to see this in profile. Plan view, I can tell where things are laid out, but seeing something in profile is a lot more descriptive. So I can right click on flow paths and select add, and you'll see if I hover over, my cursor turns green. I'll select this manhole and I'll select the downstream most point, and you can click escape to stop drawing, and we have a magenta flow path which is outlined. So now right click on flow path and show profile, and scroll with your middle mouse cursor and you can zoom in and examine this network. You'll probably notice a couple things right off the bat. That these manholes aren't set at the correct elevations relative to these pipe connections. And you'd be right. That's something that I purposely overlooked when we originally imported using the GIS option, as I didn't synchronize these manholes. Let's do that now. So under the preliminary sizing tab, there's an option that says synchronize manhole inverts. As easy as that. I'll bring this profile back on the screen, and we'll see that it automatically set these manhole inverts to the pipe inverts. So another way that XPDrainage tries to be helpful to clean up erroneous or missing data. So the next thing we might want to do is we might simply want to size the pipe network. So we can do this a couple ways. Under preliminary sizing, we could select the pipe sizing wizard, or under connections, you'll see there's a pipe sizing wizard option right here. So the first thing we need to do in order to use the pipe sizing wizard is we have to have a flow path. What we'll notice is that all of the connections in that flow path and all tributaries within that system, we might call those branch lines, will all be sized together. So in this case, when I show this magenta flow path, all of this network and all of the associated tributaries will all be sized. So essentially, this entire network will be sized in one go. So we only have one flow path. So I'm going to select next. And now we can pick what kind of design criteria we follow. So in this case, I'm going to use this IDF table from Greenville. I'm going to select the 10-year storm from that table. And we'll notice we have a pipe sizing library, which is loaded. So if we have to upsize, it will jump to the next largest size in this list. Something else we'll be doing is we'll be locking the slopes and the inverts. There's lots of options that you could play with. In this case, we only want to upsize the diameter of these pipes. So based on the inflows, which will be calculated based on the rational method and the preliminary sizing details of those inflow areas, will upsize the diameters of these pipes. By default, we have this synchronized manhole inverts, so that the entire manhole and pipe network is synced together. And with that, we can click Next, and we'll see a list of all of our pipe networks and items which have been adjusted. We'll see this perhaps used to be a 4-inch lateral, now is a 6-inch. Up from 6 inches, now we have a 12-inch pipe. Ultimately, select Finish, and we'll see a reporting table showing a summary of results from our sizing exercise. Now, depending on how you currently work or where you work, the default view might tell you everything you need to know. Travel time, rainfall intensity, contributing area, basically how the flow approaching each section of pipe was calculated, and ultimately the calculated velocity and capacity and flow. We could switch this to several different views, including the HEC22 standard view of this information. Again, depending on how you work and what kind of reporting you like to have, everything as detailed as the HEC22 report or as simple as kind of our default reporting are all options. To this point, we've sized our pipe network. We've laid out a good starting point for our arch underground detention system. Last thing we can do is we can validate our analysis. Under Analysis, Validate. And this will call out potential issues in our model. So what we'll find here is, if I expand these, there's a problem with levels. And it says the outlet is lower than the connection. So if I select this item, it will upsize that elevation slightly to make it on par with the adjacent object. When I moved the catchment area, so I reassociated where this where this inflow drains to. There was an inlet which used to be associated here. We're just going to say remove that unconnected item. So that's kind of something we might always do. So if I say apply, okay, the model is complete, and we can now run a full hydrograph hydraulic analysis on this network. And that concludes Chapter 2 of the Introduction tutorial for XPDrainage.